Close your eyes and feel the ground beneath you. Right now, as you settle into comfort, something extraordinary waits in the darkness below. The floor you rest upon. The foundation of your home. The solid earth that has always been there. All of it sits like a thin shell over chambers so vast they could swallow entire cities. These are not empty caves. They are not simple hollow spaces carved by water or wind. These chambers pulse with liquid rock. They breathe with the slow rhythm of geological time. They hold enough molten stone to reshape continents. And they have been gathering this power for thousands upon thousands of years. You cannot see them. You cannot hear them. But they are there, patient as sleeping giants, waiting beneath every step you take. The word supervolcano feels heavy on the tongue. It sounds violent and frightening. But tonight, let that word transform in your mind. Let it become something different. Something beautiful. A supervolcano is not a mountain that explodes. It is not a cone-shaped peak like you might imagine. It is something far more mysterious and elegant. Picture instead a chamber. A vast underground cathedral made of stone. Its ceiling arches high above pools of glowing orange liquid. This liquid moves slowly, like thick honey warmed by sunlight. It swirls and eddies in patterns older than human memory. The walls shimmer with heat, painted in colors that no human artist could ever capture. This is magma. Liquid rock. It flows through tunnels and caverns that stretch for miles beneath the surface. It carries the Earth's memories. Every grain of sand that was once a mountain. Every shell that was once a living creature in ancient seas. Every crystal that formed in darkness over millions of years. All of it melted together, flowing like a river of time itself. You might wonder how rock becomes liquid. How something so solid and permanent can melt like ice cream on a summer day. The answer lies in the Earth's great secret. Our planet is not the cold, lifeless ball of stone it appears to be from space. Deep inside, it burns with the heat of creation. Imagine peeling an apple. The thin skin represents the crust we live on. The flesh underneath represents the mantle. This mantle is hot. So hot that rock becomes soft like warm clay. It moves and flows, though so slowly you could watch for a lifetime and never see it shift. Sometimes, this flowing rock finds pathways upward. It rises like warm air on a cold morning. It gathers in pockets and chambers, collecting drop by drop over centuries. These chambers grow larger. The pressure builds. The temperature rises. And slowly, patiently, a supervolcano is born. But birth is not the right word. That suggests something sudden and quick. Supervolcanoes do not appear overnight like flowers after rain. They develop over geological time. Time measured not in human lifespans, but in the rise and fall of entire species. Time measured in the creation and erosion of mountain ranges. Time measured in the slow dance of continents across the surface of our planet. The chamber beneath Yellowstone National Park began forming 2 million years ago. Before humans learned to use fire. Before ice ages came and went. Before the ancestors of modern trees ever took root. The magma has been collecting there, growing stronger and more powerful, while life evolved and changed on the surface above. Think of it as the Earth's savings account. Energy deposited slowly over unimaginable periods. Heat stored like sunshine captured in stone. Pressure building gradually, without hurry, without urgency. Just the patient accumulation of power that could, when the time comes, change the entire world's climate. Right now, 15 of these chambers exist around our planet. 15 sleeping giants. Some rest beneath national parks where families take photographs and children chase butterflies. Others hide beneath lakes so peaceful that their surfaces reflect clouds without a ripple. Still others wait beneath forests where deer drink from crystal streams and birds sing in ancient trees. You have probably walked above one without knowing it. Driven over roads that cross their boundaries. Breathed air that once circulated through their underground halls. The supervolcanoes are not separate from your world. They are part of it. They are the foundation upon which your entire world rests. Scientists have given them names like old friends. Yellowstone sleeps beneath Wyoming's wilderness. Toba rests under a lake in Indonesia, its surface so calm it mirrors the sky perfectly. The Phlegraean fields stretch beneath the busy streets of Naples, Italy, where people drink coffee and children play soccer above chambers of liquid stone. Each one is different. Each has its own personality, its own rhythm, its own way of breathing. Some are young and restless. Others are ancient and patient. Some stir occasionally, sending small earthquakes through the ground like sighs in sleep. Others rest so deeply that decades pass without the slightest movement. But they all share one remarkable quality. They are all connected to the same source of power. The same heat that warms the deepest parts of our planet. The same energy that moves continents and raises mountains. The same force that has been shaping and reshaping our world since the very beginning of time. Tonight, as you rest above this hidden realm, let yourself feel connected to something larger than your daily worries. Something more permanent than tomorrow's plans. Something as patient and enduring as the Earth itself. The supervolcanoes remind us that our planet is alive. Not alive like a plant or animal, but alive with movement and energy and change. They remind us that the ground beneath our feet is not solid and permanent as it seems. It is part of a living system. A system that breathes and moves and transforms, though so slowly that human eyes cannot perceive its motion. We are passengers on a dynamic planet, traveling through space on a world that continues to create and recreate itself. The magma far below you continues its ancient dance. It swirls and flows, carrying heat from the Earth's core toward the surface. It whispers stories of pressure and temperature, of chemistry and physics, of forces that operate on scales both impossibly large and intimately small. And as you drift toward sleep, suspended between the vast chambers below and the infinite sky above, you become part of this story. Part of the Earth's great breathing. Part of the slow, eternal rhythm that connects all things. But these sleeping giants do not sleep forever, and their awakening holds secrets that could change everything we know about our planet's climate. Imagine a world map spread before you like a gentle quilt. Each continent rests in its familiar place. The oceans flow in their ancient basins. Everything appears peaceful and still. But scattered across this map, like sleeping guardians, 15 special places hold power beyond ordinary understanding. These are the supervolcanoes. Each one rests quietly in its chosen corner of the world. Each one dreams in geological time, where 1,000 human lifetimes pass like a single season. Tonight, you will meet them one by one, learning their names and their stories like greeting old friends who have watched over our planet since before human footsteps ever marked the Earth. Begin your journey in the American West, where Yellowstone stretches across 3 states like a peaceful wilderness kingdom. Families visit here every summer to watch geysers shoot steam into the blue sky. Children point excitedly at bubbling hot springs painted in impossible colors. Parents take photographs of bison grazing in meadows that seem to stretch forever. But beneath this postcard beauty lies something magnificent. The Yellowstone supervolcano sleeps under the entire park. Its chamber stretches 30 miles across and 5 miles deep. If you could drain it like a bathtub, you could fit the entire city of Los Angeles inside with room to spare. Yet visitors walk above it every day, completely unaware of the liquid rock flowing slowly in cathedral-like spaces far below their feet. Travel now across the Pacific Ocean to Indonesia, where tropical islands rise from warm blue waters like emeralds scattered on silk. Here, Lake Toba reflects perfect white clouds in its mirror-smooth surface. Fishermen paddle wooden boats between floating villages. Children swim in water so clear you can see smooth stones resting on the bottom. This peaceful lake fills the caldera of another sleeping giant. 74,000 years ago, Toba awakened and changed the entire world's climate. Ash from that eruption traveled across continents, painting sunsets orange for years afterward. But now it rests again, dreaming underwater so calm that dragonflies use it as a landing strip for their delicate wings. Journey next to Italy, where the Phlegraean fields hide beneath the bustling city of Naples. Here, people drink espresso at sidewalk cafes. Vendors sell fresh tomatoes and bright lemons in outdoor markets. Children chase soccer balls through narrow streets lined with ancient buildings. Few realize they live above chambers of molten rock that stretch beneath their homes and schools and shops. The supervolcano breathes so gently that most residents never feel its subtle movements. Only sensitive instruments can detect its slow, deep sighs as magma shifts in darkness far below the city's foundations. Cross the ocean to New Zealand, where Lake Taupo sparkles like a blue jewel set in rolling green hills. Vacationers come here to fish for trout that swim in water fed by underground springs. They hike trails through forests where native birds sing songs older than human memory. They never suspect that this peaceful lake marks the location of one of the world's most powerful volcanic systems. The Taupo supervolcano last erupted 1800 years ago, but its sleep has been so deep and quiet that sheep now graze peacefully on grass growing from soil enriched by ancient volcanic ash. The lake reflects mountains and clouds with such perfect clarity that sometimes visitors cannot tell where the water ends and the sky begins. Each of these sleeping giants has its own personality, its own rhythm of rest and dreams. Some stir occasionally, sending small earthquakes rippling through the ground like a sleeper shifting under covers. Others rest so deeply that decades pass without the slightest movement or sound. Scientists monitor them all with the patience of devoted guardians. They place sensitive instruments around each caldera like doctors listening to a patient's heartbeat. They measure ground movement smaller than the width of a human hair. They analyze gases that escape from hot springs and fumaroles, reading chemical signatures like letters in an ancient language. What they have discovered is remarkable. These supervolcanoes do not operate on human schedules. They do not wake up suddenly like alarm clocks ringing in the morning. Instead, they follow patterns measured in hundreds of thousands of years. Some have erupted 3 or 4 times since they were born. Others have awakened only once or twice in their entire geological lifetime. The Long Valley caldera in California has been quiet for over 700,000 years. It sleeps beneath snow-capped mountains where skiers glide down powdery slopes in winter and hikers pick wildflowers in summer meadows. Hot springs still bubble up through cracks in its rim, but these are gentle reminders of the vast energy resting far below, not signs of immediate awakening. In Siberia, the massive Siberian traps represent a supervolcano so ancient that its eruptions helped shape the very atmosphere we breathe today. Now it rests beneath endless forests where brown bears lumber through birch groves and rivers run clear and cold toward the Arctic Ocean. The land shows no obvious signs of its volcanic past, yet deep below, the geological machinery that once changed the world's climate remains intact. These 15 giants share more than just size and power. They share a connection to the deepest parts of our planet. Each one taps into the heat that has been flowing upward from the Earth's core since our world was young. Each one represents a window into forces that operate on scales so vast they humble human imagination. But perhaps most remarkably, they share a gift for patience that teaches us about the true nature of geological time. While human civilizations rise and fall, while languages are born and forgotten, while species evolve and adapt to changing conditions, the supervolcanoes simply continue their slow, deep breathing. They remind us that our planet operates on timescales that make human history seem like a brief moment. The pyramids of Egypt, the Great Wall of China, the oldest living trees on Earth, all of these represent mere seconds in the geological day during which these sleeping giants have been gathering their strength. Yet they also remind us of our connection to something larger and more enduring than our individual lives. Every breath you take contains molecules that have passed through their ancient chambers. Every glass of water you drink holds atoms that have been heated and cooled by their underground fires. You are part of their story, just as they are part of yours. As you rest tonight, carried by the rhythm of your own quiet breathing, 15 giants rest with you, their massive chambers rising and falling in the slow cadence of geological sleep. But what forces stir in those depths, and how does liquid rock begin its patient journey toward the surface where it might one day touch the sky? Close your eyes and imagine descending through layers of stone, deeper than any elevator could carry you, deeper than any mine shaft has ever reached. Here, in the warm darkness far below your resting place, something beautiful is happening. Something that has been happening since before the first snowflake fell, before the first flower bloomed, before the first breath of wind stirred the first leaf on the first tree. Molten rock is beginning its journey upward. This liquid stone does not rush like water flowing down a mountainside. It does not hurry like wind racing across an open field. Instead, it moves with the patience of honey on a cold morning, thick and golden and unhurried. Each drop carries stories written in minerals and crystals, tales of pressure and time that stretch back millions of years. Picture this magma as it begins to stir in chambers so deep that the weight of the entire world presses down upon it. The temperature here reaches 2000 degrees Fahrenheit, hot enough to melt copper pennies, hot enough to turn solid granite into liquid as smooth as cream. Yet this heat does not burn with the wild energy of a forest fire. It glows with the steady warmth of the Earth's own heart. The magma moves because it must. Deep below, where the Earth's core spins like a great furnace, heat radiates outward in invisible waves. This heat warms the rock above it, making it less dense, lighter than the cooler stone that surrounds it. Like a bubble rising slowly through thick syrup, the hot rock begins its ancient pilgrimage toward the surface. But this is not a simple journey. The path upward winds through a maze of stone corridors that have taken millions of years to form. Some passages are wide as cathedral halls, their walls polished smooth by countless flows of liquid rock. Others narrow to cracks so thin that magma must squeeze through them drop by precious drop. As the molten rock rises, it carries with it the memory of its birthplace. Crystals of olivine and pyroxene float within it like tiny green and black jewels, each one formed under pressures that would crush any surface material to powder. These crystals tell the story of the deep Earth, of temperatures and pressures that exist nowhere else in our solar system except in the hearts of planets. The magma also carries gases dissolved within its glowing mass like bubbles waiting to form in a slowly warming glass of soda. Water vapor mingles with carbon dioxide and sulfur compounds, all held in solution by the immense pressure of the overlying rock. These gases will play their own important role in the story, but for now they remain invisible passengers on this upward journey. Sometimes the rising magma encounters barriers in its path. Layers of harder rock block its way like dams across a river. When this happens, the liquid stone does not force its way through with violence. Instead, it waits. It pools in underground chambers, gathering strength and heat, growing larger as more magma arrives from below. These chambers become the Earth's patient storage rooms. Here, the magma rests and changes, cooling slightly, allowing some crystals to settle toward the bottom while lighter materials rise toward the top. The chamber becomes layered like a cake, with different compositions at different depths. Some layers are rich in silica, making them thick and sticky. Others contain more iron and magnesium, giving them a darker color and thinner consistency. Time moves differently in these underground halls. 1,000 years might pass while the magma chamber grows by just a few feet. 10,000 years might go by as temperatures slowly rise and new batches of molten rock arrive from below. The chamber breathes with geological time, expanding and contracting as the Earth's crust shifts and settles above it. You can think of these chambers as the Earth's slow cookers, preparing ingredients that have been mixing for longer than human civilization has existed. The heat and pressure work their chemistry with infinite patience, transforming ordinary rock into something capable of extraordinary things. Sometimes, chemical reactions occur within the magma that change its very nature. Iron combines with oxygen to form new minerals. Silicon links with aluminum to create complex crystal structures. The liquid rock becomes a laboratory where the fundamental building blocks of our planet are constantly rearranged and reformed. As more magma arrives from below, the pressure within the chamber slowly builds. The overlying rock begins to bulge upward, rising so gradually that even the most sensitive instruments can barely detect the movement. Mountains grow taller by inches spread across centuries. Lakes become slightly shallower as their floors lift imperceptibly toward the sky. The magma chamber becomes like a balloon slowly filling with air, but a balloon made of rock and surrounded by more rock, expanding against forces that would crush any material made by human hands. The pressure builds not with explosive suddenness, but with the steady persistence of geological processes that have shaped our planet since its birth. Within the magma, the dissolved gases begin to play their part in this ancient drama. As the liquid rock rises toward lower pressures, these gases start to come out of solution, forming tiny bubbles that make the magma foam like champagne opened after years in a cellar. But even this happens slowly, gently, with the measured pace of all things geological. The bubbles make the magma lighter, helping it rise more easily through the remaining rock above. They also make it more powerful, like adding yeast to bread dough. The gas-filled magma becomes capable of moving obstacles that once seemed immovable, but it does so with patience rather than violence. As the magma continues its upward journey, it encounters different types of rock, each with its own story to tell. It melts some stones completely, incorporating their minerals into its flowing mass. It heats others just enough to make them soft and pliable, bending them like clay in a potter's hands. The liquid rock also encounters water in the surrounding stone, water that has been trapped in tiny pores and cracks for thousands of years. This water becomes steam when it meets the hot magma, adding more gas to the already bubbling mixture. The interaction between water and molten rock creates some of the most beautiful minerals on Earth, crystals that will one day sparkle in museum displays or catch sunlight in a collector's careful hands. Through all of this, the magma maintains its steady upward progress. It follows the path of least resistance, finding ways around obstacles, seeping through weaknesses in the rock, always moving toward the surface with the patience of geological time. Each foot of progress might take decades. Each mile might require centuries. But the journey continues, driven by forces as fundamental as gravity and heat, as persistent as the turning of the Earth itself. And far above, where you rest in peaceful sleep, the surface world continues its daily rhythms, unaware of the slow pilgrimage taking place in the darkness below. But what happens when this patient journey finally reaches its destination, when the rising magma encounters the surface world and the ancient chambers can no longer contain their fiery contents? Imagine watching a flower close its petals at the end of a long summer day. The delicate edges fold inward slowly, gracefully, returning to the center with quiet acceptance. This gentle surrender holds a secret about one of the most powerful geological events on Earth. When a supervolcano awakens, the land above it performs a similar dance, folding inward with surprising grace. This is not the violent explosion most people imagine when they think of volcanic eruptions. This is something far more beautiful and mysterious. This is the birth of a caldera, a word that comes from the Spanish word for cauldron, but sounds much softer when you let it rest on your tongue like a gentle prayer. Picture a mountain standing tall against the sky, its slopes covered with pine trees and wildflower meadows. Animals make their homes in the forests that climb its sides. Streams carry snowmelt down through valleys carved by thousands of years of spring runoff. Everything appears permanent and solid, as mountains always do to human eyes. But deep below this peaceful scene, the magma chamber that has been growing for millennia finally reaches a critical moment. The pressure has built beyond what the overlying rock can contain. The gases dissolved in the molten stone have expanded like bread rising in a warm oven. The chamber has grown so large that its roof begins to crack under its own weight. What happens next unfolds not with sudden violence, but with the measured pace of geological processes. The mountain does not explode like a bomb. Instead, it begins to empty from within, like a balloon slowly deflating or a soap bubble releasing its air. The magma finds pathways to the surface through cracks and fissures that have been forming for decades. It rises through these channels, carrying with it the gases and heat that have been building pressure for so long. As the molten rock flows upward and outward, the chamber below begins to empty. And as the chamber empties, something remarkable happens. The mountain above it loses its foundation. The solid rock that once seemed so permanent discovers that it has been resting on a hollow space all along. Slowly, gracefully, like a building settling into soft ground, the mountain begins to sink. This settling does not happen all at once. It occurs in stages, like a curtain falling in slow motion. First, small sections of the mountain's peak begin to subside. Cracks appear in the ground, but they open so gradually that trees continue growing beside them, their roots finding new paths through the shifting soil. As more magma flows out of the chamber, larger sections of the mountain follow it downward. The process accelerates, but even at its fastest, it moves with geological patience. What seems rapid in Earth's terms might take days or weeks in human time, allowing life to adapt and respond to the changing landscape. The mountain's collapse creates something entirely new. Where once a peak reached toward the sky, now a great bowl begins to form. This depression grows wider and deeper as more of the overlying rock settles into the space once occupied by molten stone. The edges of this bowl become the rim of the caldera, marking the boundary between the collapsed center and the still-standing surroundings. Picture this process like watching a soufflé fall in an oven, but stretched across a timescape that makes human history seem like a single heartbeat. The collapse is thorough but gentle, creating not destruction but transformation. The mountain reshapes itself into something entirely different, something that will serve new purposes in the landscape. The caldera that forms can be enormous. Some stretch 20 miles across, large enough to hold entire cities within their boundaries. Others are smaller, intimate enough that you could walk across them in an afternoon. But all share the same origin story of patient pressure, gradual emptying, and graceful collapse. As the land settles, it creates a natural collection basin. Rain that once flowed down the mountain slopes now pools in the center of the caldera. Over time, this water forms lakes that reflect clouds and sky in their still surfaces. The collapsed land becomes a cradle for new ecosystems, a protected space where different forms of life can flourish. The rim of the caldera becomes a natural amphitheater, its walls rising in gentle curves that frame the lake below. These walls tell the story of the collapse in layers of rock that once formed deep parts of the mountain's interior. Geologists can read these layers like pages in a book, each one representing a different chapter in the mountain's long life. But the caldera is not a scar on the landscape. It is not a wound that needs healing. Instead, it becomes one of the most beautiful and peaceful places on Earth. The protected bowl creates its own weather patterns, often staying calm when winds rage outside the rim. The lake that forms in its center becomes a mirror for passing clouds and migrating birds. Wildlife discovers the caldera quickly. Deer come to drink from the new lake. Fish find their way into the water through streams that flow down from the rim. Birds build nests in the protected environment, raising their young in safety. The caldera becomes not an ending, but a beginning. Native peoples often considered these places sacred, understanding instinctively that they represented powerful transformations in the Earth's surface. They built their ceremonies around the calm lakes and gentle slopes, recognizing the special energy that seems to gather in these circular spaces. Modern visitors feel this same sense of peace when they stand on a caldera's rim. There is something deeply satisfying about the circular symmetry, the way the eye can trace the entire boundary of this natural bowl. The mind finds rest in the gentle curves and the still water at the center. Scientists study calderas with special fascination because they represent one of the few places where the Earth's interior processes become visible on the surface. The collapsed land reveals rock formations that once lay miles underground. Hot springs and fumaroles continue to connect the caldera to the heat source below, creating windows into the planet's deep chemistry. Each caldera has its own personality, shaped by the type of rock that collapsed and the amount of magma that was released. Some have steep walls and deep lakes. Others slope gently toward shallow ponds. Some remain hot and active, with steaming vents and warm springs. Others cool completely, becoming indistinguishable from ordinary valleys except for their perfect circular shape. The formation of a caldera marks not the end of a mountain story, but its transformation into something new and different. The land that once reached toward the sky now cradles the sky's reflection. The solid peak becomes a container for liquid. The upward-reaching mountain becomes a bowl that gathers and holds. This transformation happens throughout the geological world, creating some of the most peaceful and beautiful landscapes on our planet. Crater Lake in Oregon fills a caldera so perfectly round that it seems drawn with a compass. The lake's surface sits like a blue jewel in its circular setting, so still and clear that visitors often mistake reflections for reality. And as the caldera settles into its new shape, as water fills its center and life begins to flourish on its slopes, something else begins to happen in the atmosphere high above. The ash and gases released during the mountain's gentle transformation begin their own journey, carrying messages that will travel around the entire world. Picture a single grain of volcanic ash, smaller than the tiniest seed, lighter than a whisper, rising high above the caldera where it was born. This microscopic traveler carries within its glassy structure the memory of molten rock, the story of pressure and heat, the essence of deep earth chemistry. It begins a journey that will take it around the world, touching lives and landscapes thousands of miles from where it first saw daylight. The ash does not travel alone. Millions of its companions join the voyage, lifted by columns of hot air that rise like invisible elevators into the sky. These columns, called plumes, carry their precious cargo higher than commercial airplanes fly, up into the stratosphere where the air is thin and the winds blow strong and steady. You can think of these ash particles as the Earth's own form of mail, messages written in silicon and minerals, addressed to every corner of the planet. Each grain contains information about the volcano's chemical composition, the temperature at which it formed, the gases that were present during its creation. Scientists can read these messages years later, decoding the volcanic stories written in stone dust. As the ash rises through the atmosphere, it encounters different layers of air, each with its own personality and purpose. Near the ground, the air swirls and eddies with local weather patterns. Higher up, steady winds flow like rivers in the sky, carrying their burden eastward or westward depending on the season and the location of the eruption. The stratosphere becomes the ash's highway. Here, 15 to 30 miles above the Earth's surface, the air is so thin that commercial jets cannot fly, but winds can circle the globe with remarkable consistency. The volcanic particles join these high-altitude currents like passengers boarding a cosmic train, settling in for a journey that may last months or even years. From this great height, the ash grains become artists of the sky. They scatter sunlight in ways that transform ordinary sunsets into masterpieces painted across the heavens. The tiny particles filter out certain colors while allowing others to pass through, creating the deep oranges and brilliant reds that make people stop in the middle of their evening walks to stare in wonder at the sky. You may have witnessed these volcanic sunsets without realizing their origin. Perhaps you stood in your backyard watching the sun disappear behind buildings or trees, marveling at colors so intense they seemed almost artificial. The beauty you observed might have been created by ash from an eruption on the other side of the world, particles that traveled across oceans and continents to paint that particular evening sky just for you. The ash affects more than just the colors of sunset. As it drifts through the stratosphere, it begins to influence the very climate of our planet. Each particle acts like a tiny mirror, reflecting a small portion of the sun's energy back into space before it can reach the Earth's surface. Individually, each grain accomplishes almost nothing. Together, millions upon millions of them can cool the entire planet. This cooling happens gradually, gently, like drawing thin curtains across a bright window. The Earth receives slightly less solar energy, and temperatures drop by small but measurable amounts. The change is subtle enough that most people never notice it directly, but sensitive instruments can detect the difference, and climate scientists can track the ash's influence on weather patterns around the world. The particles also interact with water vapor in the atmosphere, becoming the centers around which ice crystals and water droplets can form. They seed clouds that might not have existed otherwise, creating weather patterns that ripple outward from their presence like stones thrown into a still pond. Rain falls in places that might have remained dry. Storms form along paths they might not have followed. As the ash continues its global journey, it begins to settle back toward Earth. Some particles fall quickly, landing in nearby forests and fields within days of the eruption. Others remain aloft for months, circling the globe multiple times before gravity finally draws them downward. The largest grains settle first, while the finest dust stays suspended longest, painting sunrise and sunset skies for years after the eruption that created them. When the ash finally reaches the ground, it becomes a gift to the soil. Volcanic particles are rich in minerals that plants need to grow strong and healthy. Potassium, phosphorus, and trace elements that took millions of years to concentrate in magma chambers now spread across the landscape like natural fertilizer. Farmers in regions that receive volcanic ash often find their crops growing more vigorously, their harvests more abundant. The ash creates layers in the soil that geologists can read like pages in a history book. Each eruption leaves its signature in the ground, a thin line of volcanic material that marks a moment in geological time. Scientists can dig through these layers, dating them and mapping the patterns of ancient eruptions, learning how supervolcanoes have influenced climate throughout Earth's history. In some places, thick deposits of volcanic ash have created entirely new landscapes. The fine particles cement together over time, forming soft rock that water and wind can carve into fantastic shapes. Entire cities have been built in caves carved from volcanic ash deposits, their inhabitants living comfortably in rooms hollowed from stone that once drifted as dust high above the earth. The ash connects us all in ways both seen and unseen. The breath you draw into your lungs as you rest tonight may contain particles that traveled halfway around the world. The soil that grew the food you ate today may have been enriched by ash from eruptions that occurred before your grandparents were born. The spectacular sunset you admired last week may have been painted by dust from a volcano you will never visit, in a country whose name you might not even know. This connection extends through time as well as space. The ash falling today will influence the weather patterns your children experience. The particles settling into lake beds and ocean floors will become part of the geological record that future scientists will study to understand our current climate. Each grain carries messages not just from the volcano that created it, but from the atmosphere it traveled through, the weather it influenced, the places it touched. Ocean currents catch some of the ash, carrying it to depths where it settles among the remains of tiny sea creatures. Here, mixed with shells and microscopic skeletons, the volcanic particles become part of the seafloor, adding their chemical signatures to sediments that will someday rise again as new mountains form and continents shift. The ash also tells stories of resilience and adaptation. Plants learn to grow in volcanic soils. Animals adapt to the temporary changes in their environment. Human communities develop traditions around the cycles of eruption and recovery, building cultures that honor both the destructive and creative powers of volcanic activity. Each particle that drifts through the high atmosphere carries with it the potential to influence lives it will never directly touch. The ash becomes a messenger of global connection, a reminder that events in one part of our world can ripple outward to affect the entire planet. It speaks of systems too large and complex for any single mind to fully comprehend, yet intimate enough to touch each sunset and each breath. As you rest beneath this vast atmospheric ocean, millions of microscopic travelers continue their journeys overhead, carrying stories from distant fires, painting tomorrow's dawn with colors borrowed from yesterday's eruptions. But these tiny messengers are not the only gifts that supervolcanoes give to our planet's climate, and their influence reaches back through time to touch the very origins of human civilization. Close your eyes and step backward through time, beyond the reach of written history, beyond the oldest stories passed down through generations, beyond the first cities and the first farms. Journey with me to a morning 74,000 years ago, when the sky above our early ancestors began to change in ways they had never seen before. The humans living then looked much like you. Their hearts beat with the same rhythm. Their eyes sought the same comfort in familiar faces. Their hands reached for the same warmth when cold winds blew. They were your ancestors, carrying within their bodies the genetic heritage that would someday become yours, living their daily lives with the same hopes and fears that still move through human hearts today. On that ancient morning, families gathered around fires just as people still do. Children played games that made them laugh. Adults shared stories and planned for tomorrow. The sun rose in the east as it always had, painting the African landscape in shades of gold and amber that have never changed across all the millennia. But far to the north, across the ocean in what we now call Indonesia, Mount Toba was beginning its greatest eruption. The magma chamber that had been growing for hundreds of thousands of years finally emptied itself into the sky, sending columns of ash and gas higher than any mountain, higher than clouds ever climb, up into the stratosphere where winds could carry its burden around the entire world. Your ancestors could not have known what was happening thousands of miles away. They had no instruments to detect the ash beginning its global journey. No weather forecasts warned them of changes coming to their skies. They simply lived their lives as humans always have, trusting that tomorrow would bring the same sun, the same sky, the same patterns of weather they had always known. But within days, the first signs of change began to appear. The sunsets grew more brilliant, painted in colors deeper and more intense than anyone living had ever witnessed. The sky took on hues that made people pause in their daily tasks to stare upward in wonder. Elders might have searched their memories for similar events, finding nothing in their experience to match what they were seeing. As weeks passed, the changes became more noticeable. The sun seemed dimmer during the day, as if a thin veil had been drawn across its face. Temperatures began to drop slightly, not enough to cause immediate alarm, but enough that people pulled their animal skins a little tighter around their shoulders when the evening winds began to blow. The volcanic winter had begun. This phrase sounds harsh and frightening, but the reality unfolded with the same patience that characterizes all geological processes. The cooling happened gradually, over months and years rather than days. The dimming of sunlight was subtle, the kind of change that reveals itself slowly, like the progression of seasons but stretched across a much longer time frame. Your ancestors adapted as humans always have, with intelligence and cooperation and remarkable resilience. When familiar plants became scarce, they learned to find nutrition in new sources. When their usual hunting grounds grew less productive, they explored new territories. When cold weather lasted longer than expected, they developed better ways to stay warm and preserve food. The genetic studies tell us that humanity's population declined during this time, compressed by the challenging conditions into smaller, more scattered groups. But they also tell us something far more important and beautiful. They tell us that these groups survived. That they not only endured the volcanic winter, but emerged from it stronger and more adaptable than before. Every person alive today carries genetic evidence of this survival. The DNA flowing through your blood contains molecular proof that your ancestors possessed the resourcefulness and determination to outlast one of the most significant climate events in human history. Their resilience lives on in your cells, a microscopic inheritance more precious than any treasure. During the darkest years of the volcanic winter, when ash still painted the sunsets and temperatures remained cool, your ancestors developed innovations that would shape the future of humanity. They refined their tool-making techniques, creating more efficient implements for hunting and gathering. They strengthened their social bonds, sharing resources and knowledge in ways that helped entire communities survive. They also developed new forms of art and storytelling, ways of preserving and passing on the wisdom they gained during these challenging times. Around fires that burned a little brighter against the cooler air, they shared stories that helped make sense of their changing world. They created music that brought comfort during long, cold nights. They painted images on cave walls that still speak to us across 74,000 years. The children born during the volcanic winter grew up in a world different from the one their parents had known. But they grew up nonetheless, playing games adapted to new conditions, learning skills suited to their changed environment. They laughed and loved and dreamed of their own futures, just as children always have. Their adaptability and hope became part of the human inheritance they passed on to the next generation. As the years slowly passed, the ash began to settle from the atmosphere. The sun grew gradually brighter. Temperatures started their slow return to previous levels. The volcanic winter was ending, not with sudden warmth, but with the same patience with which it had begun. Your ancestors watched these changes with the wisdom that comes from surviving great challenges, understanding that stability and change are both part of life's natural rhythm. The end of the volcanic winter marked not just a return to easier times, but the beginning of a new chapter in human development. The populations that had survived spread out from their refuges, carrying with them the knowledge and innovations they had developed during the difficult years. They brought new technologies, new ways of organizing their communities, new stories and songs and artistic traditions. These human communities began to explore and settle new territories with a confidence born from having survived one of Earth's greatest tests. They had learned that they could adapt to almost any conditions, that human creativity and cooperation could overcome challenges that seemed impossible. This knowledge became part of their cultural inheritance, passed down through generations as a deep understanding of human resilience. The genetic diversity that survived the Toba eruption became the foundation for all future human populations. Every innovation, every artwork, every love story that followed can trace its origins back to the communities that endured the volcanic winter. The music you enjoy, the technologies you use, the capacity for hope and creativity that defines human nature, all of it flows from ancestors who refused to surrender to a darkened sky. Today, when you face your own challenges, you carry within yourself the same genetic inheritance that helped your ancestors survive the aftermath of the largest volcanic eruption in human history. Their determination lives in your DNA. Their resourcefulness flows through your bloodstream. Their hope beats in your heart. The volcanic winter ended as slowly as it had begun, but it ended with something new, the knowledge that humans could survive anything the Earth might offer, and that survival often leads to growth and innovation beyond what anyone could have imagined. But the Toba eruption was not unique in its ability to change the climate, and the cooling it created was just one example of how volcanic chemistry can transform the very air we breathe. High above your resting place, where the air grows thin and the sky fades from blue to black, an invisible ballet is taking place. Molecules so small they could never be seen with the naked eye are performing a dance that has the power to cool entire continents. This is chemistry at its most elegant and essential, a process that has been regulating our planet's temperature for millions of years. The dancers in this atmospheric ballet are sulfur compounds, released from volcanic eruptions and carried upward by columns of rising air. Each molecule is perfectly designed by nature to interact with sunlight in ways that human chemists are only beginning to understand. They move through the stratosphere like graceful performers, each playing their part in a symphony of cooling that operates on a global scale. Picture a single sulfur dioxide molecule, invisible to your eyes but vital to your world's climate. This simple combination of one sulfur atom bonded to two oxygen atoms carries within its structure the ability to transform the very character of Earth's atmosphere. As it rises through the layers of air, it begins a chemical transformation as beautiful and precise as any choreographed dance. In the stratosphere, 20 miles above the surface, the sulfur dioxide encounters water vapor that has made its own journey upward from the oceans and lakes below. These two substances combine in the presence of sunlight, creating something entirely new, tiny droplets of sulfuric acid suspended in the thin air like microscopic jewels. Do not let the word acid frighten you. These are not the harsh chemicals of industrial processes, but nature's own delicate creations, so dilute and perfectly balanced that they become agents of healing rather than harm. Each droplet is smaller than the finest mist, lighter than the breath you exhale as you sleep, yet collectively they possess the power to regulate the temperature of an entire planet. These acid droplets become the Earth's own sunglasses, filtering the intense solar radiation that would otherwise warm the surface below. They do not block the sun completely, but rather scatter its light in all directions, sending a portion of the solar energy back into space before it can reach the ground. The process is gentle and gradual, like drawing sheer curtains across a bright window. The cooling effect begins slowly, building over months as more sulfur compounds rise from volcanic sources and undergo their atmospheric transformation. The droplets spread around the globe, carried by stratospheric winds that circle the Earth with remarkable consistency. What began as gases released from a single volcanic source becomes a worldwide network of natural climate control. Scientists have discovered that this sulfur-based cooling system is remarkably sophisticated. The size of each droplet is precisely tuned by natural processes to reflect sunlight most efficiently. Too small, and they would have little effect. Too large, and they would fall back to Earth too quickly to influence global climate. But nature creates them at just the right size, about half a micron across, perfect for their role as atmospheric regulators. The droplets also interact with other chemicals in the stratosphere, creating a complex web of reactions that scientists are still working to understand. They provide surfaces where other atmospheric compounds can undergo transformations that would be impossible in empty air. In this way, they become catalysts for a whole series of chemical processes that help maintain the delicate balance of our planet's atmosphere. As you rest beneath this invisible protective layer, you are benefiting from one of nature's most elegant engineering solutions. The sulfur compounds work tirelessly, 24 hours a day, reflecting excess solar energy back into space whenever the Earth begins to warm too rapidly. They require no maintenance, no human oversight, no external power source. They simply do their work with the quiet efficiency that characterizes all of nature's best designs. The beauty of this system lies not just in its effectiveness, but in its responsiveness. When large volcanic eruptions inject massive amounts of sulfur compounds into the stratosphere, the cooling effect intensifies proportionally. The Earth's atmosphere automatically adjusts to counteract the increased volcanic activity, maintaining global temperatures within ranges that allow life to flourish. This natural thermostat operates on timescales that span from seasons to decades. The sulfur droplets remain suspended in the stratosphere for 1 to 3 years, depending on their size and the altitude at which they form. During this time, they continue their work of reflecting sunlight, gradually settling toward lower altitudes where they are eventually washed from the atmosphere by rain. The chemistry of cooling extends beyond simple reflection of sunlight. The sulfur droplets also influence the formation of clouds by providing additional surfaces around which water vapor can condense. These volcanic clouds often have different properties than ordinary clouds, reflecting sunlight more efficiently and lasting longer in the sky. They become part of an intricate feedback system where volcanic activity influences weather patterns around the globe. Temperature measurements from around the world show the elegant precision of this natural cooling system. After major volcanic eruptions, global temperatures typically drop by 1 to 2 degrees Fahrenheit, enough to influence growing seasons and weather patterns, but not enough to threaten the basic stability of Earth's climate. The cooling effect peaks about 2 years after the eruption, then gradually diminishes as the sulfur compounds settle out of the atmosphere. The chemistry of volcanic cooling has operated throughout Earth's history, helping to regulate our planet's temperature through periods of intense volcanic activity and relative quiet. Ice core samples from Greenland and Antarctica preserve chemical evidence of major eruptions going back hundreds of thousands of years, each one leaving its signature in the frozen record of our planet's atmospheric chemistry. Modern climate scientists study these natural cooling processes with deep appreciation for their sophistication. The sulfur-based climate regulation system represents a level of complexity and responsiveness that human technology is only beginning to approach. It operates without any central control, yet responds to changing conditions with remarkable precision and effectiveness. The molecules themselves tell a story of perfect adaptation to their environment. Their chemical structure allows them to remain stable in the harsh conditions of the stratosphere while still being reactive enough to form the acid droplets that provide cooling. They are neither too stable nor too reactive, but perfectly balanced for their role in the Earth's climate system. As you drift toward sleep, these invisible guardians continue their chemical ballet overhead. They dance with photons of sunlight, transforming solar energy into scattered light that paints the sky in subtle hues. They interact with water molecules, creating droplets that serve as mirrors for excess heat. They move with wind currents, distributing their cooling influence across continents and oceans. The sulfur compounds remind us that chemistry is not just a laboratory science, but a living, breathing part of our planet's daily operations. Every breath you take, every ray of sunlight that warms your face, every raindrop that falls from the sky has been touched by chemical processes operating on scales both impossibly small and magnificently large. But this atmospheric chemistry represents only one part of a larger story, for while sulfur compounds cool the Earth from above, life itself has learned to thrive in the shadows of volcanic winters, adapting and flourishing in ways that reveal the profound resilience woven into the fabric of our living world. Imagine a forest where ash falls like gentle snow, coating every leaf and branch with a fine grey dust. The air is cooler than usual, and the sun seems dimmed by a thin veil of particles floating high above. To human eyes, this might appear to be a landscape of hardship, a world temporarily made hostile by forces beyond anyone's control. But look closer, and you will discover something remarkable happening beneath this volcanic blanket. Life is not merely surviving here. Life is quietly adapting, innovating, and even thriving in ways that reveal the profound resilience woven into the very fabric of our living world. Each plant, each animal, each microscopic creature carries within itself the accumulated wisdom of millions of years of evolution, including countless previous encounters with volcanic winters and climate changes. The trees in this ash-dusted forest demonstrate nature's gentle genius for adaptation. As volcanic particles settle on their leaves, they might initially struggle with the reduced sunlight filtering through the hazy atmosphere. But within days, many species begin to adjust their photosynthesis processes, becoming more efficient at capturing the available light. Their leaves orient themselves differently, angling toward any bright spots in the filtered sky like solar panels adjusting to changing conditions. Some trees actually benefit from the mineral-rich volcanic ash that accumulates around their roots. The ash contains potassium, phosphorus, and trace elements that have been concentrated deep within the earth for millions of years. As rain gradually washes these nutrients into the soil, the trees receive a slow-release fertilizer more complex and balanced than anything humans could create. The forest floor tells its own story of quiet persistence. Mushrooms and other fungi, already adapted to low-light conditions, continue their essential work of decomposing fallen leaves and recycling nutrients. Many species of fungi actually increase their activity during volcanic winters, taking advantage of the slightly acidic conditions created by the ash. They form new partnerships with tree roots, sharing nutrients and information through underground networks that connect the entire forest in ways invisible to surface observers. Small mammals demonstrate perhaps the most touching examples of adaptation during these challenging times. Squirrels learn to cache different types of food when their usual acorns and nuts become scarce. Mice develop new foraging patterns, often working together more cooperatively than they would under normal conditions. Their fur grows thicker as temperatures drop, and their metabolisms adjust to make the most of whatever food they can find. Birds show remarkable flexibility in their response to volcanic winters. Some species that normally migrate long distances delay their journeys or alter their routes to take advantage of new food sources that appear as ecosystems shift. Others discover that the cooler temperatures create ideal conditions for insects they rarely encounter during normal years. Their songs often become more complex during these periods, as if the challenging conditions inspire greater creativity in their communication. Even the insects, though smallest and seemingly most vulnerable members of the ecosystem, reveal extraordinary adaptive abilities. Many species enter deeper states of dormancy, slowing their metabolism to conserve energy until conditions improve. Others accelerate certain life cycle stages, taking advantage of the unique chemical conditions created by volcanic ash to complete reproduction more quickly than usual. The most remarkable adaptations often occur at the microscopic level, invisible to casual observation but essential to the ecosystem's continued functioning. Bacteria in the soil adjust their chemical processes to work with the new mineral composition created by volcanic ash. Algae in streams and ponds develop enhanced abilities to photosynthesize in reduced light conditions. These tiny organisms form the foundation of food webs that support all larger life forms. Aquatic ecosystems show their own forms of resilience during volcanic winters. Lakes and rivers may receive inputs of ash and change runoff patterns, but aquatic life adapts with remarkable flexibility. Fish alter their feeding behaviors, often discovering new food sources in the sediment stirred up by ash deposits. Aquatic plants may grow more slowly in reduced light, but they often become more efficient at nutrient uptake, making better use of the minerals introduced by volcanic activity. The persistence of life during volcanic winters reveals something profound about the nature of living systems. They possess an inherent flexibility that allows them to bend without breaking, to find opportunity within challenge, to discover new possibilities even when familiar patterns are disrupted. This resilience is not accidental but represents millions of years of experience with environmental change. What makes these adaptations even more remarkable is how they often lead to innovations that benefit ecosystems long after the volcanic winter has ended. Plants that develop more efficient photosynthesis methods during periods of reduced sunlight often retain these improvements when normal light returns. Animals that learn new foraging strategies frequently continue using these techniques, expanding their ecological niche. Ecosystems that successfully navigate volcanic winters often emerge more diverse and resilient than they were before. The social behaviors of many species also evolve during challenging periods. Animal communities often become more cooperative, sharing resources and information more freely than during abundant times. These strengthened social bonds frequently persist after conditions improve, creating more stable and supportive animal societies. The challenging times become opportunities for developing deeper connections and more effective communication systems. human communities living near active volcanic regions have learned similar lessons from observing nature's response to volcanic winters. Traditional cultures often developed agricultural practices that mimicked the adaptive strategies they observed in wild ecosystems. They learned to diversify their crops, store resources more effectively, and strengthen community bonds during difficult periods. The timing of natural cycles also demonstrates life's ability to synchronize with volcanic patterns. Many plant species have evolved reproductive cycles that take advantage of the unique soil conditions created after volcanic ash deposits settle. Some flowers bloom more abundantly in the springs following volcanic winters, as if celebrating the return of normal conditions with extra enthusiasm. Even the genetic level reveals evidence of life's long relationship with volcanic activity. Many species carry genes that are activated only during periods of environmental stress, producing proteins and enzymes specifically designed to help organisms cope with the chemical and physical changes associated with volcanic winters. These genetic tools remain dormant during normal times but spring into action when needed, like emergency supplies stored in a closet until circumstances require their use. The recovery phase following volcanic winters often produces some of nature's most spectacular displays of abundance. The combination of cool temperatures, enriched soils, and strengthened ecological relationships frequently leads to periods of exceptional growth and reproduction. Forests may grow more vigorously, wildflower displays may be more abundant, and animal populations may expand rapidly as they take advantage of improved conditions. This pattern of challenge followed by renewal mirrors many aspects of human experience. Just as ecosystems find ways to not merely survive but actually grow stronger through difficult periods, humans too possess the capacity to transform challenges into opportunities for growth and increased resilience. The quiet persistence of life during volcanic winters teaches us that adaptation does not require dramatic or violent change. Most successful adaptations happen gradually, gently, through small adjustments that accumulate over time into significant transformations. Nature shows us that resilience is not about resisting change but about flowing with it while maintaining essential identity and purpose. As you rest in your own safe space tonight, you can take comfort in knowing that you are part of this same living world that has demonstrated its ability to thrive through every form of environmental challenge Earth has offered. But how do the scientists who study these remarkable systems learn to read the subtle signals that reveal when sleeping giants might stir, and what technologies help us listen to the Earth's gentle warnings? Deep in a quiet laboratory, far from the sleeping giants they study, scientists sit before glowing screens that display the heartbeat of our planet. Lines of data flow across their monitors like electronic poetry, each wave and spike telling stories of movements so subtle they occur below the threshold of human perception. These researchers have become translators of Earth's most intimate language, learning to read messages written in seismic waves and ground movement smaller than the width of a human hair. Picture a seismometer, one of hundreds scattered around the world's supervolcanoes like sensitive ears pressed to the ground. This remarkable instrument can detect vibrations so faint they would be completely invisible to your senses, movements that occur when underground magma shifts position or when gases escape through tiny cracks in the Earth's crust. Each tremor, no matter how small, creates a signature that travels through the rock like ripples spreading across a still pond. The seismometer transforms these invisible vibrations into visible patterns on computer screens, creating what scientists call seismograms. These charts look like the traces made by a hospital machine monitoring a patient's heartbeat, with regular rhythms interrupted by occasional spikes and variations. Each pattern tells a story about what is happening deep underground, written in a language that has taken decades of careful study to understand. When you see a seismogram from a quiet volcanic region, the traces appear almost flat, with only tiny irregularities marking the constant background trembling that occurs as the Earth settles and adjusts. But scientists have learned to read meaning into even these subtle variations. A slight increase in the frequency of small earthquakes might indicate that magma is beginning to move far below the surface. A change in the type of seismic waves could suggest that underground chambers are slowly expanding. Around each major supervolcano, networks of these sensitive instruments create a web of listening posts that monitor every subtle change in the Earth's behavior. The instruments communicate with each other and with central monitoring stations through invisible radio waves and satellite connections, creating a nervous system that spans continents and operates 24 hours a day. The scientists who interpret this data have developed an almost mystical ability to recognize patterns in the Earth signals. They can distinguish between the seismic signature of a truck driving past a monitoring station and the barely perceptible tremor caused by magma moving 30 miles underground. They learn to recognize the unique voice of each volcanic system, understanding that Yellowstone whispers differently than Toba, that each sleeping giant has its own characteristic way of stirring in its rest. But seismometers are only one type of instrument in the scientists' toolkit for reading Earth's pulse. GPS stations scattered around volcanic regions can detect ground movements so small they measure less than the thickness of a coin. These movements occur as underground magma chambers slowly expand or contract, causing the surface above to rise or sink by tiny amounts over periods of months or years. Imagine the ground beneath Yellowstone National Park rising by just 2 inches over the course of a decade. To visitors hiking the trails or watching geysers erupt, this change would be completely invisible. But to the sensitive GPS instruments monitoring the area, this gentle uplift tells a clear story of magma movement and pressure changes occurring in the vast chamber below. The GPS stations work by communicating with satellites orbiting high above the Earth, measuring their position with precision that would have seemed impossible just a few decades ago. Each station knows its location to within fractions of an inch, and any change in that position gets recorded and transmitted to scientists who study the patterns of ground movement like doctors monitoring a patient's vital signs. Thermal monitoring represents another way scientists listen to the Earth's quiet communications. Infrared cameras and temperature sensors can detect changes in heat emission from volcanic areas, often revealing underground activity long before any other signs become apparent. A hot spring that grows slightly warmer, a patch of ground that begins melting snow a little earlier in the spring, a fumarole that starts releasing more steam, all of these thermal changes speak of deeper processes at work. Gas monitoring provides yet another window into underground volcanic activity. Scientists have learned that different gases escape from magma at different stages of its journey toward the surface. By analyzing the chemical composition of gases released from hot springs and volcanic vents, researchers can determine whether underground magma is becoming more active, moving closer to the surface, or changing its chemical composition. The instruments that measure these gases are marvels of modern chemistry, capable of detecting trace amounts of sulfur compounds, carbon dioxide, and other volcanic gases in concentration so small they measure in parts per million. Changes in gas composition often provide the earliest warning signs of increasing volcanic activity, sometimes years before any other monitoring systems detect changes. What makes this global monitoring network truly remarkable is how all these different types of measurements work together to create a comprehensive picture of volcanic activity. A slight increase in seismic activity might be meaningless by itself, but when combined with subtle ground deformation and changes in gas emissions, it begins to tell a coherent story of what is happening in the hidden depths below. The scientists who interpret this data approach their work with the patience of archaeologists and the precision of musicians tuning delicate instruments. They understand that the Earth signals unfold over timescales far longer than human attention spans, and that meaningful patterns might take months or years to reveal themselves clearly. Many of these researchers spend their entire careers learning to read the language of a single volcanic system. They become intimately familiar with its normal patterns of behavior, its seasonal variations, its responses to external influences like changes in atmospheric pressure or distant earthquakes. This deep familiarity allows them to recognize when something unusual is beginning to happen, even when the changes are so subtle that automated systems might miss them. The monitoring stations themselves often become peaceful refuges in wild landscapes. Solar panels power the sensitive instruments while weather stations record local conditions that might influence the measurements. The equipment operates continuously, sending its data streams to distant laboratories where scientists maintain their patient vigil, watching for signs of change in systems that might rest quietly for thousands of years between major episodes of activity. This technological symphony of measurement and monitoring represents humanity's attempt to develop a conversation with geological processes that operate on timescales vastly different from our own. The instruments serve as translators, converting the Earth's slow geological language into information that human minds can process and understand. Through this network of sensitive ears pressed to the ground, scientists have learned that the Earth is constantly communicating, constantly sharing information about the deep processes that shape our planet's surface and influence its climate. As these patient watchers continue their electronic vigil, monitoring the slow pulse of sleeping giants around the world, they help us understand our place in a larger story that connects the deepest parts of our planet to the air we breathe and the climate that surrounds us. But what does this understanding mean for our future, and how do we find peace in living alongside forces so much larger and more patient than ourselves? As you settle into the comfort of your own quiet space tonight, 15 sleeping giants rest with you, their vast chambers breathing slowly beneath landscapes where children play and flowers bloom. These ancient forces that have shaped climate and carved continents continue their patient slumber, operating on timescales so vast that human history appears as brief as a single season in their geological year. The morning sun will rise tomorrow over Yellowstone, painting the geysers and hot springs in golden light. Families will gather around Old Faithful, watching steam shoot skyward with the same wonder that has drawn visitors for generations. Children will skip stones across peaceful lakes, never suspecting that they play above one of Earth's most magnificent underground cathedrals, where liquid rock dreams in darkness 30 miles below their laughter. In Indonesia, fishermen will paddle their boats across Lake Toba's mirror-smooth surface, casting nets into water that fills a caldera formed by the greatest eruption in human memory. The lake reflects clouds and sunrise colors with perfect clarity, holding no visible trace of the volcanic winter that once touched every corner of the Earth. Life has returned, flourished, and created beauty from what was once considered catastrophe. The Italian families living above the Phlegraean fields will begin their day with espresso and fresh bread, conducting the daily rituals of life above chambers that could someday reshape the Mediterranean. Their ancestors have lived here for thousands of years, building cities and raising families in full knowledge of the volcanic forces below, finding peace through understanding rather than fear. This is perhaps the most beautiful lesson the supervolcanoes teach us, that understanding transforms our relationship with forces beyond our control. When we learn about the patient timescales on which these systems operate, when we understand the monitoring networks that listen constantly to their quiet breathing, when we appreciate the role they play in regulating our planet's climate, fear gives way to something deeper and more sustaining. The scientists who dedicate their lives to studying these sleeping giants understand this transformation intimately. They spend decades learning to read the subtle signals of geological change, developing relationships with volcanic systems that span entire careers. Their monitoring stations scattered around the world create a network of patient watchfulness, listening to the Earth's pulse with instruments more sensitive than any human sense. These researchers find peace in their work not because they can predict exactly when major eruptions might occur, but because they understand the vast timescales involved. They know that the probability of witnessing a supervolcanic eruption during a human lifetime is incredibly small. They understand that these systems provide decades or centuries of warning signs before any major activity. Most importantly, they appreciate that when these eruptions do occur, they become part of natural cycles that have been operating since our planet was young. The supervolcanoes remind us that we live on a dynamic planet, one that continues to create and recreate itself through processes both gentle and powerful. The ground beneath our feet is not static and permanent as it appears to our daily experience, but part of a living system that breathes and moves and changes, though so slowly that mountains seem eternal to human eyes. Modern technology has given us the ability to monitor these systems with unprecedented precision, but it has also revealed their fundamental patience. The GPS stations that detect ground movements measure changes so gradual they accumulate over decades. The seismometers that record underground tremors mostly register the normal background settling of a resting planet. The gas monitors that analyze volcanic emissions typically find stable compositions that change as slowly as seasons. This technological vigil creates a new kind of relationship between humanity and geological forces. We no longer face the unknown with only myths and speculation to guide our understanding. Instead, we have developed the ability to listen to our planet's own communications, to understand the signals that indicate when systems are truly changing versus when they are simply continuing their normal patterns of rest. The monitoring networks also reveal the interconnected nature of our planet's systems. When volcanic ash travels through the atmosphere, it connects distant continents through shared climate influences. When supervolcanoes rest quietly, they allow other natural systems to operate without interference. When they do become active, they demonstrate the elegant feedback mechanisms that help regulate Earth's temperature over geological time. Children growing up today will inherit this understanding along with the monitoring systems that make it possible. They will learn about supervolcanoes not as sources of fear, but as examples of the remarkable processes that make our planet unique in the solar system. They will grow up knowing that the Earth beneath their feet is dynamic and alive, connected to forces that operate on scales both impossibly large and intimately local. The future of supervolcano monitoring likely holds even more sophisticated ways of listening to our planet's communications. Satellites that can detect ground movements from space with greater precision. Underwater sensors that can monitor changes in lakes that fill volcanic calderas. Chemical analysis techniques that can read even more subtle messages in the gases released from underground chambers. But perhaps more importantly, future generations will inherit the wisdom that comes from understanding geological time. They will grow up knowing that the most powerful forces on our planet operate with patience that dwarfs human timescales. They will learn that this patience creates opportunities for preparation, for adaptation, for the development of technologies and social systems that can respond effectively to natural changes. The sleeping giants teach us about more than volcanic processes. They offer lessons in patience, in the power of slow, steady processes to create extraordinary results. They demonstrate how apparent stability and gradual change are both part of natural systems. They show us that understanding reduces fear, and that knowledge creates the foundation for wise responses to forces beyond our immediate control. Tonight, as you drift toward sleep, you can find comfort in knowing that you live in an age of unprecedented understanding about our planet's deep processes. The monitoring networks maintain their electronic vigil while you rest. The scientists continue their patient study of systems that unfold over timescales that make human civilization seem like a recent development. The supervolcanoes continue their own form of rest, their chambers filled with liquid rock that moves more slowly than honey, carrying the Earth's memories and the potential for future climate influence. They rest not with the restlessness of forces waiting to be unleashed, but with the deep peace of systems that have found their rhythm in the grand symphony of geological time. You rest knowing that understanding brings its own form of peace, and that some of the most powerful forces in our universe operate with a patience that transforms fear into wonder, uncertainty into curiosity, and the unknown into an invitation for continued learning and appreciation. In this shared rest between human consciousness and geological patience, tomorrow's quiet vigil continues, connecting your dreams to the Earth's own deep dreaming, your breath to the slow breathing of chambers filled with liquid stone, your peace to the vast peace of systems that measure time in millions of years while creating the stable foundation upon which all life depends.